Example number 5. Prove the trigonometric identity 1 minus cos theta over 1 plus cos theta is equals to, in bracket, cosec theta minus cot theta, you close the bracket, all squared. Prove the trigonometric identity. On the left hand side of the equation we have 1 minus cos theta in the numerator over in the denominator 1 plus cos theta to be equivalent to cosec theta minus cot theta all squared. If it has 1 and cos, 1 is 1 plus cos, 1 is 1 minus cos. If you see such a case, that is a case of a difference of two squares. And a case of a difference of two squares is a case of a Pythagorean identity. Are we together there? So a case of a difference of two squares from the quadratic identity, if you have a plus b times a minus b, then you are supposed to get a squared minus b. The quadratic identity, isn't it? So it means when you have the Pythagorean identity, the Pythagorean identity is a case like cos squared theta plus sine squared theta is equal to 1. So it means for you to have something like 1 minus cos theta or 1 plus cos theta, meaning you have to take cos squared theta on the other side of the equation, isn't it? So it means cos squared theta plus sine squared theta is equal to 1 is the same as sine squared theta is 1 minus cos squared theta. So in many cases, most of the trigonometric identities will be proved using the Pythagorean identity. Meaning anytime you want to prove a trigonometric identity, the first identity to be tested is the Pythagorean identity. It is the first identity which is being tested when you want to prove any trigonometric identity. Are we together? So you check the trigonometric problem you are solving. Does it have anything in relation to the Pythagorean identity? Are we together? So if you look at 1 minus cos theta and 1 plus cos theta, they are related to a Pythagorean identity. So you write down your Pythagorean identity there. We have cos squared theta plus sine squared theta is equal to 1. So that means sine squared theta is 1 minus cos squared theta. So what is 1 minus cos squared theta? 1 minus cos squared theta is a difference of two squares. Because 1 is the same as 1 squared, cos squared theta is the same as cos theta, which has been squared, isn't it? So if you have 1 squared minus cos theta squared, it's like you have a squared minus b squared. So a squared minus b squared is the same as a plus b and a minus b. Are we together there? So our a is 1 and our b is cos theta. So 1 minus cos theta squared is the same as 1 plus cos theta into 1 minus cos theta, isn't it? Meaning for us to get rid of the denominator in this given trigonometric identity, we have to use a scenario of the Pythagorean identity, isn't it? So for us to get the Pythagorean identity, we are getting a difference of two squares. So this concept of a difference of two squares is what we call the concept of the conjugates, isn't it? Meaning if you have 1 plus cos theta, the conjugate of that is 1 minus cos theta, isn't it? So you ask yourself, do you do that for the numerator? Do you get the conjugate of the numerator or the conjugate of the denominator? That is the question, isn't it? Because if you take the conjugate of the numerator, you will still get a Pythagorean identity, isn't it? If you take the conjugate of the denominator, you will still get a Pythagorean identity, isn't it? But we don't need the denominator to prove this trigonometric identity, meaning we get the conjugate of the denominator, because it is the denominator we are getting rid of, isn't it? So you take the conjugate of where you are getting rid of. If you are getting rid of the numerator, then you take the conjugate of the numerator, isn't it? But we are getting rid of the denominator, so we take the conjugate of the denominator. So in the denominator we have, if we have 1 plus cos theta, then the conjugate of 1 plus cos theta is 1 minus. So you do the same in the numerator to balance the equation, isn't it? So having done that, in the numerator you have 1 minus cos theta times 1 minus cos theta. It is a factor multiplying by itself, isn't it? So when a factor multiplies by itself, it's like it has been squared, isn't it? So in the numerator, we have 1 minus cos theta, which has been squared, isn't it? Then what do we have in the denominator? A difference of two squares, the conjugates. And those conjugates is the what? The conjugate of the Pythagorean identity, isn't it? So 1 minus cos theta and 1 plus cos theta is giving you 1 minus cos squared theta, isn't it? So from Pythagorean identity, we've shown that 1 minus cos squared theta is the same as what? It's the same as sine squared theta, isn't it? Because cos squared theta plus sine squared theta is 1. So it means sine squared theta, if you make the subject of the formula, you take cos squared theta on the other side of the equation, you get 1 minus cos squared theta. So where there is 1 minus cos squared theta, for us to get rid of that denominator, it has to be its equivalent, which is sine squared theta, isn't it? So there we now have 1 minus cos theta squared in the numerator. Then in the denominator, 1 minus cos squared theta is the same as sine squared theta. But what is sine squared theta? Sine squared theta is the short form of sine theta, which has been squared, isn't it? Are we together? Now in indices, if you have a squared over b squared, that is the same as a over b, then everything squared, isn't it? From the laws of indices, isn't it? So the whole of the numerator is squared and the whole of the denominator is squared, meaning the whole of that problem is raised to power 2, isn't it? They have a common power. Both the numerator and denominator is having a common power. So it means here we have 1 minus cos theta over sine theta, then everything is squared, because that is a common power for both the numerator and denominator. Are we together? So if you look at this for you now, you can get rid of the denominator now, because when you have a single factor in the denominator, it can easily be gotten rid of, isn't it? So a single factor in the denominator is the common denominator, isn't it? It is the common denominator. So if this is the common denominator, it's like we have 1 over sine theta minus cos theta over sine theta, then everything squared, because sine theta is the common denominator. If you have a plus b over c, that is the same as a over c plus b over c. So it means what is in the denominator is the common denominator for all the terms in the numerator, isn't it? So from here you can now see 1 over sine theta is the reciprocal of sine theta. What is the reciprocal of sine theta? Cosec theta, isn't it? So 1 over sine theta is the reciprocal of sine theta, that is cosec theta minus cos theta over sine theta. Remember, tan theta was sin over cos, isn't it? Are we together? Then it means cos over sin is the reciprocal of tan, because tan is sin over cos, but we have cos over sin, isn't it? So it means cos over sin is the reciprocal of tan, isn't it? That one becomes cot, cotangent, so that is cot theta squared. So you continue with the same process until you see that you've actually found what is on the right hand side of that equation. So proving trigonometric identity, you start from the left hand side of the equation until you reach the right hand side of that equation. So before you start proving a trigonometric identity, you must test what is being tested, isn't it? You must investigate. So like in this case, we said the first identity to be investigated anytime you are proving a trigonometric identity is the Pythagorean identity.